Good morning, guys. So today we are going to start off from the chapter thermodynamics. Okay, and as I said in the previous class, thermodynamics is actually the continuation of our previous chapter, thermal properties of matter. Right. So until and unless you have finished learning thermal properties of matter, don't even think to go for this chapter. Right. So what do you mean by thermodynamics? Thermodynamics is actually a branch of science or physics. It's actually a branch of physics which deals with the study of heat and temperature, right? It's a concept of heat and temperature and their interconversion of heat and other forms of energy. That is, see, you know what is heat. We learned in the previous chapter, and you know what is temperature. So, then along with it, right, we are going to deal or study how heat energy is converted into any other form energy and how it is going to happen, right? So there are four laws of thermodynamics, right? And it is that which governs the quantities and provide the description of any process which happens in the entire world, right? So it was William Thomson, right, in 1749, believe 1749, who made this word thermodynamics, right? And it is actually from Greek words thermos and dynamikos, right? Which means this is heat and this is powerful. From these two words, he made the term thermodynamics. Right. So, what do you mean by thermodynamics? Well, thermodynamics is a physics is a branch of physics that deals with heat, work, temperature, and their relationship to energy, radiation, physical matters, or physical properties of matter. Clear? See, later on in this chapter, we'll learn a lot of things, right? So you will learn how there are different types of processes here. There are actually in your charts for your thermodynamics. Actually, there are four laws, but you will be learning only three laws out of this. So you will learn three laws of thermodynamics, their application, and then different types of processes, as I said before. Then you will talk about engines, right? There is refrigerator, there is heat engine, there is Carnot cycle, right? This and all will be learned in this chapter, right? So it's a quite a bit large chapter, but if you understand while I'm taking, I would recommend that you learn along with me. Don't skip it, right? And previous chapter also should be studied. Okay, so let us move on. So to be specific, in thermodynamics, what we learn is how thermal energy is converted to any other form, right? And how the matter is affected during this process, right? So there is a matter or there is an object, right? And out of this, the thermal energy, or you do some process and the thermal energy is converted into some other form. So would it affect this object? And even if it's affecting is happening, how it affects, whether its temperature is getting reduced, whether its pressure increases, like that, right? Yeah. So thermal energy is energy that generates from heat, and this heat is actually generated by the tiny particles within an object, and faster these particles are moving, faster will be, or that much more the heat generated, right? So thermodynamics is not concerned of how and at what rate these energy transformations or energy changes are happening. It is only dealing with initial as amount and final amount. So how it is happening, it doesn't require to change. You in thermodynamics, we only deal about initial temperature, final temperature, initial pressure, final pressure, initial volume, final volume, like that. Clear? Only the initial and final criteria or stages are important. Similarly, this thermodynamics is a macroscopic science. Macroscopic uh, Macroscopic science. So what do you mean by macroscopic science? That is, it means only deals with bulk system, right? Bulk system means, see, I am talking about a can, right? Similarly, a can initially had a pressure P1, now its pressure dropped to P2. So I am talking about a system which is quite large, or I will say bulk, right? So I will only learn about bulk things in the case of thermodynamics, hence it is called a macroscopic science. It is not going to deal with the molecular constitution of matter. Clear? Right. So we have talked a little bit about what an introduction with respect to thermodynamics. Now, what is the difference between thermodynamics? Ah, thermodynamics and mechanics. What is the difference between it? See, in mechanics, right, we solely concentrate on the motion of particles or bodies under action of force, torque, right? Whereas in thermodynamics, it is not concerned with the motion of the system or of the motion of the particles. It only concerns of the motion of the system as a whole. It is, it, or I can say, it is not even dealing with motion. It is not at all dealing with motion. Mechanic is solely about motion. How much force I applied, how much it moved, how much force torque applied, how much accelerated it became. It is only concerned with the internal macroscopic state. How much was the initial temperature, how much is now the temperature, how much was the pressure, how much is the pressure. Clear? Right. So before moving on to the next section, I will explain this difference between mechanics and thermodynamics with an example. Right. Let us consider gun, right? And I am firing a bullet. Let's say this is a wall. I meant a wall, whatever, right? In mechanics, if a bullet is fired from a gun, we will consider the motion of this bullet, right? Then I will learn about its velocity, then I will learn about its acceleration, etc. and etc. Right? Now the same thing, right? We are going to consider a second scenario. Here, now this, let's say this bullet has struck the wall and it is falling on the wall. When it hits the wall, its kinetic energy, the bullets, kinetic energy is converted into what? Heat, right? Due to this heat generation, there will be a temperature change in temperature and internal energy of this bullet, right? These are the variables which we will learn during the thermodynamics. I hope this much is clear to find the difference between mechanics and thermodynamics. In thermodynamics, we learned how much is the velocity, acceleration, how much speed by which it is moving, etc., etc. Whereas the same scenario, and the bullet strikes the wall, its kinetic energy is converted into heat energy, right? So when this conversion is happening, how much is the temperature change and how much is the internal energy change, etc. is learned. That branch of science is thermodynamics. Clear enough? Right? I hope this much is clear now. Right. Now the next section which you are going is rather than moving on to thermal equilibrium, some of the terms which you have to know, that is different branches of thermodynamics, right? This and all are introduction for making this chapter strong, right? So thermodynamics are actually, or is 4 types. It is classified into 4. First one is classical thermodynamics. Next is statistical thermodynamics, then chemical thermodynamics, and equilibrium thermodynamics. Like that, there are 4 types of, or 4 classification of thermodynamics. Right. That is, first let's just talk about classical thermodynamics. In classical thermodynamics, the behavior of the matter is analyzed with the macroscopic approach. That is, units such as temperature, pressure, are taken into consideration, which helps the which helps us to calculate other properties, right, and to predict the characteristics of the matter that is undergoing the process. That is how the pressure is changing, how the temperature is changing, right? This and all are studied during the classical thermodynamics. This is what which we learn most of the time. That is, by using these parameters we are able to learn other properties of this system or any process which is happening, right? Whereas in statistical thermodynamics, every molecule, right, we have to learn that the properties of each and every molecule and ways in which they interact, right, are taken, or we are studying it, right? Clear? And each molecule they are learned individually, and then they are taken as a collection and then learned again, right? That is a statistical thermodynamics, right? Whereas what is chemical thermodynamics? In chemical thermodynamics, how work and heat are related to each other, right? Both in chemical reactions and in changes of states, right? While change of state is happening and during the chemical reactions, how work and heat are related, that is learned in chemical thermodynamics. This is what you will learn in your chemistry, right? Now, whereas in equilibrium thermodynamics, this is here it is a study of transformation of energy and matter. That is, while our system is approaching equilibrium, right? So there will be a little bit change in the energy and matter that is learned during the equilibrium thermodynamics. These are only a basic things which I am going to talk. Right? Clear? Now we are going to learn thermodynamics little bit detail. That is basic concepts of thermodynamics. Basic concepts of thermodynamics. That is, we are going to talk about thermodynamic terms. Some of the terms you have to learn. Right, it is having a, some of the terms are quite different when you have to learn. And basic concepts formed on this basis of these terms, right? So first term which you have to know is thermodynamic systems. Thermodynamic systems, right? Yeah. So which you learn no detail as system only. So before you go for system means no, thermodynamics is a specific portion. Suppose this is the matter, right? So the specific portion of this matter within a definite boundary, right, on which your attention is focused, right? No, suppose I am talking about a water bottle, right? So then this water bottle is having, or I am going to talk about water inside the water bottle, means this is the water and it is having a fixed boundary, right? So that means this water bottle is a system, right? Here I am only concentrated in the water which is inside the water bottle, right? And this is boundary, right? So this is called system boundary. Clear? Right. So system is a region, right, containing energy or matter that is separated from the surroundings by arbitrarily imposed walls or boundaries. I'm giving the definition again. A system is a region containing energy or matter that is separated from surroundings by arbitrary imposed walls or boundaries. Walls or boundaries. So this water inside them, water bottle, is the system now. It is arbitrarily separated from the surrounding using this boundary, right? Hence this is a system. Clear? Now system boundary. So system you have understood. So what is system boundary? Right? System boundary. A boundary is a closed surface surrounding the system which separates the system from surroundings. right? A boundary is a closed surface surrounding a system, right? Surrounding a system, right? Through which energy and mass, right? Energy and mass may enter or leave, right? So that is the definition. So again I'm repeating, a boundary is a closed, right, surface surrounding the system through which the energy, right, the energy means heat is a top of energy, right? The heat can leave or it can enter, right? So energy or heat or mass may enter or leave is known as system boundary. So what do you mean by surroundings? That is the third term. Surroundings is anything other than surroundings, okay, right? Everything that is other than the system and boundary is surroundings, right? Clear? Or everything that interacts with the system is known as surroundings. Clear? Right. So I will make an analytical figure here. Let's say this is a system, right, and this is surroundings, right? So system and surrounding can have both exchange of heat, or heat I can say, or I will say heat energy, or you can do work. So there can be to and fro. Let's make this like a to and fro arrow, right? There will be exchange of heat, right? Clear? Right? So this is system, the boundary of system, system boundary, right? This is anything other than system is surrounding. So actually I can say this part and all are surrounding itself. Clear? Right? So there are different type of system. System we are going to learn little bit in detail. Clear? Now talking about systems. Systems itself is having basically three type of classification are there. One is open system or types, right? Then closed system, and the third one is isolated system. So mainly there are three types of systems we have to learn, which is open system, closed system and isolated system. Open system, see, you are having water inside a pan and you are keeping it on a fire so that the water is boiling, right? I would say this is an open system. Why? In this system there is both exchange of energy and matter. Energy means, in a sense, see, when I heat the water of this the water is boiling, right? So I can say water is converting into vapor. So I would say there is matter exchange, right? Now heat exchange is of course there, right? Heat is getting transferred from here to here. Then after boiling, the heat is getting transferred from here to here, right? So there is both the exchange of matter as well as energy. Those type of system is known as open system. Clear? Easy. Now then what will be closed system? Right. See here, the exchange of matter does not take place, but exchange of energy takes place. That is, there is a conversion or exchange of energy is happening, but not the what? Matter. That is, example, let us say that balloon, right? It is filled with gas, right? So similarly a pot with the lid, right? So gas balloon, right? So here there is exchange of what? Energy, because the balloon is rising up, right? So that I can say, since it is rising, because there is an energy conversion between the system and the surroundings, right? Whereas similarly, if I take a pot with the lid closed, right? This is a pot and there is a lid also over it, right? In this case, the heat is being transferred from the gas stove to the pot, right? And also the heat is getting transferred or exchanged with the surroundings, right? Whereas the matter, that is the water vapor or what's inside this container, is not able to escape. Why? Because it is closed with lid. So there is exchange of heat but not matter. Exchange of heat is there. The balloon, right? You are burning fuel, right? So the exchange of you are giving heat to it so that the balloon rises up, right? But there is no exchange of what? Matter. Yeah, so this is a closed system. The last type of system we have to learn is isolated system. Right? Isolated, simple. There is neither exchange of heat nor matter. Our flask, thermo flask, right? Any closed insulated vessel, right? This example is thermos flask, where you keep your no the hot water to remain hot, or to remain, the tea will be remaining hot itself for a period of time, right? So when you in the thermos you keep tea, right? So for many hours it is keeping hot itself. Why? Because the walls of the thermos are insulated, right? Insulated in sense they do not allow the heat to be exchanged with outside, neither the matter exchange happens, right? So that is an example of isolated system. So how many type of systems are learned now? Open system, closed system, and isolated system, right? Similarly, the depending upon the boundaries, right? Boundary of a system, also there are different type of walls. One is adiabatic wall, then the other is diathermic wall. These are all terms you have to learn before you jump into thermodynamics. Right, after that we have to talk about little bit other things, then only we would straight away go for the law of thermodynamics, right? And similarly, zeroth law of thermodynamics I have already told about it in the previous section, so I recommend zeroth law of dynamics. You can write it by yourself, you can read in your book and write it, okay? Right, then we will go for state variables, etc. So what do you mean by adiabatic wall? So it is an insulated wall which does not allow heat to flow from one system to another. That is, suppose I have a section here A and B, I am having a wall. Let's say this is an adiabatic wall. Let's say A, this section is having pressure P1, volume V1. Say this, the pressure is P2. Let's say its volume is V2. Let's say A is at temperature T1 and B initially is at a temperature T2. And I am saying, I hope you understood, there is an adiabatic wall. Let's say there is an adiabatic wall here also, right? That is, this entire thing is separated from the surroundings using an adiabatic wall, right? So what happens is, adiabatic wall doesn't allow any type of heat exchange, neither heat exchange nor matter exchange with the surrounding, nor there is a matter exchange or heat exchange between these two systems, right? So there is no exchange of heat. So if this system or A is at temperature T1, then that temperature T1 remains as it is. If this system or B is having temperature T2, then its temperature also remains the same, right? Because there is no exchange of heat. That is, both are at their own respective temperature. No change in temperature with time, right? So there is no heat flow between A and B, right, as they are separated by an adiabatic wall, and both these systems are also separated from the surroundings by an adiabatic wall, which means there is no heat flow between A and the surroundings and B and its surroundings. Clear? Right? Clear? Right. So adiabatic wall, no exchange of heat or energy or matter in a sense. Clear? This is our thermal flask, right? It is having a adiabatic wall, right? So the next type of wall is diathermic wall, right? So what is diathermic wall? Means conducting wall, right? Diathermic means conducting wall, right? So which allows heat exchange between two systems. Same. If A and B, and I'm saying there is an conducting wall or diathermic wall between them, P1 V1, P2 V2, right? Clear? Now let's say this one is having higher temperature and this is having lower temperature T2, then exchange of heat happens from A to B. Heat flows from here to here. So there is exchange of heat, right? And as the heat flows from higher temperature of the system to the lower temperature till the system attains equilibrium. Both of them have same temperature, this flow happens, right? Clear? So this is an example of diathermic wall. So diathermic wall means conducting wall. Adiabatic wall means which doesn't allow the exchange of heat nor matter. Clear? So this and all are the common terms which you have to know while you learn thermodynamics. Now I'm just starting or going to talk about zeroth law. We have talked about it. Zeroth law means there are three systems, A, B and C, right? If A is in thermal equilibrium with C, B is in thermal equilibrium with C, then A and B are thermal equilibrium with each other. I have talked about it, right? So I recommend you to write the exact theorem from your textbook, right? So there are something more I had to continue from here, right? So we have talked about heat capacity or thermal capacity. Then we have talked about specific heat. Then we have talked about molar specific heat, right? And after that we talked about our what type of exchange of state, that is fusion, then melting, etc., right? And there is another term which you have to learn in thermodynamics, which I will mix it up, okay, which is latent heat, right? Latent heat. I believe latent heat you might learn in, actually it is in thermal properties. I don't remember. I hope it is from thermal properties itself. So latent heat. So I told you thermal properties, thermodynamics and kinetic theory of gases comes in single topic as per physics. In your textbook, I recommend you to look where latent heat is, right? So latent heat. So you know that an object can be supplied heat to raise its temperature, right? So similarly, we can, or amount of heat can be supplied or it can be removed. Heat can be removed, right? That amount of heat which is supplied or removed can cause that object to change its state. That is, solid can change to liquid or liquid can change to gas and vice versa, right? It can happen like this, or this motion also happens, right? So when you give heat to a solid, it converts to liquid. Again heated, liquid changes to gas. Whereas if you are removing heat from gas, it becomes liquid. Removing heat from liquid, it becomes solid, right? So I can say that whenever heat is given or heat is taken, there happens change of state, right? Clear? So at constant temperature, so this and all are going to happen in constant temperature. So written, if you ask what is the definition of latent heat, the amount of heat that has to be supplied or removed from a body for its complete change of state at constant temperature is called latent heat of body. The amount of heat that has to be supplied or removed from a body for its complete change of state at a constant temperature is called latent heat of body, and its unit is calorie per gram, right? That is in the CGS system. SI system, it is joules per kilogram, right? And its dimension formula is m0 L square T raised to minus 2. Right, it is having, actually it is the same dimension as that of the gravitational potential. You see, you can understand is having the same dimension as that of the gravitational potential. Just means something I am going to make you remember, that's it. Now there are two types of fusion or latent heat you have to learn. First is latent heat of fusion. Now latent heat is showed by L, and to show it as latent heat of fusion, I write it as L suffix F. Right. Now what do you mean by latent heat of fusion? Latent heat of fusion is a quantity of heat which is required to change a unit mass of solid, right, substance at its melting point completely into liquid at the same temperature. That is, if solid is at T degree Celsius, then liquid should be also, if it is converted to liquid, that liquid also will be at T degree Celsius itself, right? The amount of heat, right, or required to change unit mass means 1, right? Unit mass of a solid substance at its melting point completely to a liquid at same temperature, then that is known as latent heat of fusion, right? Or I can even say in the back side order also. See, this way. The definition I am going to change. The amount of quantity of heat required to freeze unit mass of liquid at its freezing point completely into solid at the same temperature is known as latent fusion. Right? See, I'm going to give an example for it. Let us take water and ice. Right. So for ice, that is your solid. Right. For ice, what is its melting point? 0 degrees Celsius. Right. Right. So at 0 degrees Celsius, the ice, it is the melting point 0 degrees Celsius. Right. Why it is said to be 0 degrees Celsius? Freezing point itself is called melting point value. Freezing point itself is your melting point. Right. That is your, hope you understood what is the same or what is the meaning of it. See, when you consider water at 0 degrees Celsius, it starts to become ice, right? Right, that is its freezing point. Right, now that is the same temperature when the ice can come back to water form also. That is the exact point. Below 0 degrees Celsius, that is -1, -2, -3, etc., that during that temperature entirely it is ice itself. So just above 0 degrees Celsius, the ice can just change into water. Right, so freezing point and melting point are same. I hope you understood. Right. So ice at 0 degrees Celsius, that is its freezing point, right? It converts to liquid, right? So I have to give it some heat, right? Some heat, that is a unit mass. Let's say I have taken it as 1 gram, right? I have taken 1 gram of ice at 0 degrees Celsius, which is its what? Melting point. Right, I have to give some, let's say x amount of calories so that it will convert into liquid form, which is water. Right, at what degree Celsius? At 0 degrees Celsius. Right, so 1 gram of ice, when I give x amount of energy, the ice at its melting point 0 degrees Celsius converts into water at 0 degrees Celsius. Now it has been found that it is actually X is 80 calorie. Right? Again I am describing it. If 1 gram of ice at 0 degrees Celsius is given 80 calorie of heat, it converts to water at 0 degrees Celsius. Right, so that means 80 calorie per gram is the latent heat of fusion. Clear? Right, now this in joules, that is SI unit, it is 336 joules per gram or 336 kilojoules or 336 kilojoules per kilogram. Means I just converted it. Clear? Right? Right. So similarly, I can talk about water. Water at its freezing point, that is 0 degrees Celsius. Right? When it is supplied with 80 calorie, and water is how much gram? 1 gram. This unit mass. When I supply or I take from it 80 calorie, when I take a heat of 80 calorie from water of 1 gram at 0 degrees Celsius, it converts to ice at 0 degrees Celsius. Right? That means latent heat of fusion of water to ice is 80 calorie per water to ice or ice to water, both are same. LF is 80 calorie per gram. Clear? Now that 80, or you can write Q, the amount of energy supplied or removed, is equal to M, if M mass of an object is taken, into LF. Right? If M is the mass of the body and LF is the latent heat of fusion, then the quantity of heat required to change the body into, or a solid body into liquid at melting point or solid at freezing point, liquid to solid, is Q is equal to M into LF. Clear? Simple. Right? It's very important concept, guys. See, if we are having m grams of ice, let's say m grams of ice, right? Let's say it is at 0 degrees Celsius, right? And I am going to mix it with m grams of water below 80 degrees Celsius. Below 80 degrees Celsius. When the resultant, you will get in a mixture, right? It will be partly ice and water, but the temperature will be 0 degrees Celsius. Keep that in mind, right? Similarly, if I take m grams of ice at 0 degrees Celsius and I am mixing it with m grams of water at 80 degrees Celsius, then the resultant will be water at 0 degrees Celsius. Because less than 80 degrees Celsius means its latent heat is not reached. Right? Keep that in mind. Right? Similarly, if m grams of ice, which is at 0 degrees Celsius, if I mix it with n grams of water above 80 degrees Celsius, right, then the resultant will be water above 0 degrees Celsius. Water above 0 degrees Celsius. Right? Right? But not the 80 degrees Celsius. It will be just above 0 degrees Celsius. Clear? So these three criteria, I don't know where you're going to write, but these 3 points should be there in your mind. Well, let's repeat what we have just learned. If I am mixing equal mass of ice with water, right, ice is always 0 degrees Celsius, but water, if the temperature of the water is less than 80 degrees Celsius, then the resultant will be both ice and water at 0 degrees Celsius. If the temperature of water is equal to 80 degrees Celsius, you will get the resultant mixture will only have water at 0 degrees Celsius. If ice and water in such a way that the water is having higher temperature than 80 degrees Celsius, then you will get water at water which is having temperature greater than 0 degrees Celsius, but not as greater as 80 degrees Celsius. Clear? So this much 3 things should be there in your mind registered. Right. The next is latent heat of vaporization. So since you have understood latent heat of fusion, latent heat of vaporization is also very easy. So vaporization means here 2 things which you have to learn is liquid and gas. So what is latent heat of vaporization? This is the quantity of heat which is required to convert unit mass of liquid at boiling point, right? At boiling point completely into a gaseous state at the same temperature. Or you can say amount of heat required to convert unit mass of gas at its condensation point or condensation temperature completely into liquid at the same temperature, right? Same as that of ice and so condensation point and boiling point are the same, which is 100 degrees Celsius in the case of water. Let us talk about water and water vapor. Let us say I am going to take water and we are going to consider 1 gram of water. And let's say the water is at 100 degrees Celsius. Right? Now I require heat, right? 1 gram of water is there, right? Let's say it is 100 degrees Celsius. Now I require some heat, right, to convert this water into water, or I can say steam. Let us just write it as steam, right? So while I convert, the steam also will be at 100 degrees Celsius itself, right? So I require to convert 100 degrees Celsius water to 100 degrees Celsius steam. And how much calorie I will require? I will require 550 calorie for the same. Similarly, if I want to convert 100 degrees Celsius steam to 100 degrees Celsius water, 540 calorie of heat has to be absorbed out. Clear? Right? Right. Now, I'm not going to go in detail since you can understand from here itself. Now, just like the previous case, when ice and steam, right? Clear? So, let's say m grams of ice is there, right? Let's say it is at 0 degrees Celsius. If I mix it with n grams of steam at 100 degrees Celsius, right? Now the resultant will be mixture of water and steam, right, at 100 degrees Celsius, right? Similarly, well, guys will ask me, this is ice, this is steam, so intermediate step of water is missing. So that's why the point which I am going to take now is very important. See, let's say we are having a mass m substance, right, and let's say it is in solid state, right, and let's say its fusion point is TF, right? Now I want this solid to be purely converted into m mass of gas, not liquid, right? So, and I want that gas to be at its boiling point, let's say TB, right? Clear? So how much minimum amount of heat I have to supply? Keep this very important point. Q. First I have to first convert solid into what? Liquid, right? So I have to first conversion or change of state. So it is m into LF. Why? Solid to liquid. So latent heat of fusion, right? Plus. Now let's say solid is at a temperature, let's say its temperature is what? Fusion temperature, right? Or freezing temperature, TF, right? Then I have to convert it into vaporization, right? So, or I can say boiling point has to be reached, right? Clear? So keep this in mind. So first, now I have to convert from the liquid, which is, let's say, now solid was at some temperature, same temperature the liquid is, the conversion has been happened. Now I have to increase the liquid's temperature, which was at TF, to what temperature? TB, right? So I am raising temperature, so there is a delta T, right? So that means now Q, when I convert the liquid to liquid itself, liquid to liquid's boiling point. If you want, I will draw it in a structural way. First, solid at its fusion temperature or freezing temperature, converted to liquid, right, at freezing temperature. Now I want to convert it into liquid at its boiling point. Then from here I want to make it into a gas at its boiling point. This is what I want, right? Clear? So this part from here to here we have done. We have converted from solid to liquid at its freezing point or fusion point. Plus Now I want to change the temperature of the liquid itself. So there is no change of phase, right? Or state is not changing. So M into, right, specific heat of water or liquid, right? So let's take it SL into delta T becomes what now? TB minus TF. TB minus TF, boiling point, or it can be written as TV, right? TV means vaporization, same boiling point itself, right? Plus, now this stage has happened. Now I want to change from liquid to gas. Liquid to gas means there is a change in state. So it is MLV. What is it? LV, that is latent heat of vaporization. This is the minimum amount of heat required for conversion from solid to gas. Solid at freezing point to gas at boiling point or vaporization point. Clear? Right? Simple. This is, I have not written the terms, guys. This is a values I have just written. Clear? Right? Now, similarly, suppose in another section there is a solid, right? Let's say it is at set temperature T1, right? It is not reached its freezing point, right? And I want to convert it into a gas, right, to a temperature, let's say T2, and this temperature is greater than the boiling point of gas, right? Say again, I'm repeating, solid is at a temperature T1 which is less than its freezing point, and gas, I want to convert it to gas which is having a higher temperature than the boiling point or vaporization point, right? So how much minimum heat has to be supplied? Q is equal to, so intermediate steps, I hope you remember. If you're not, I will draw it. So I want to first convert the solid at higher lower temperature T1 to the solid form itself, but its freezing point has to be reached, right? From here I have to first convert it into liquid, right, to the same temperature TL. Now from liquid to liquid itself, but at a higher temperature of its boiling point has to be reached. From there it has to be changed to the gas at the boiling point, right? Now from gas it has to reach the gas, or you have to make the, or raise the gas temperature to what? T2. This much steps has to be reached. Now let us write the equation Q. Solid to solid itself, so M, right? M grams I'm going to write. M, specific heat of what? Solid, into delta T is what? I'm raising the temperature, so TF minus T1 plus, this stage is over. I'm converting from solid to liquid, so phase change or the states change, that is ML fusion, MLF, plus, now this stage is finished, right? Now I want to raise the temperature of the liquid, that is MS liquids TB minus TF, right? This temperature is over, or this section is over. Now I want to change from liquid to gas, so MLV, that is vaporization. Now this stage is over. Now I want to raise the temperature MC, so not C, S now, S of gas, delta T is T2 minus TB, right? This is how we are supposed to write. Clear? In examination, these and all will be having a specific values, guys. Clear? Right. I hope you understood how to write the question. Right. This is a very important section, guys. I hope you understood. Clear? Now, we'll do a small problem. Suppose 0.1 kilogram, 0.1 kilogram of copper. Copper nails are said to be heated to 100 degrees Celsius. And it is heated now to 100 degrees Celsius, and then we are going to drop this copper into 0.25 kilogram of paraffin, right, which is at 29 degrees Celsius. Right, 0.1 kilogram copper heated to 100 degrees Celsius, dropped into 0.25 kilogram of paraffin, which is at 29 degrees Celsius. If the maximum temperature of the system, right, is 33 degrees Celsius, calculate the specific heat capacity of the paraffin, and you are given the specific heat capacity of copper as 380 joules per kilogram per Kelvin. Right? So how would you do this question? So I will start doing it. See, how much is heat lost by the copper is the heat gained by the paraffin. That is something which has to be registered in your mind. Right? So let us talk about how much heat is lost by the copper nails. Copper does have any phase change? No, it is not changing its state. So it is only losing its heat. So heat lost by copper nails, that is ms delta T, right, that is equal to 0.1, right, into what is specific heat of copper, 380 delta T. Initially it was at 100 degrees Celsius, and uniformly its temperature has dropped to 33, means now its temperature change is 100 minus 33, that is 67, right? What is the change? Right? So you will get 2926 joules. Right. Now what is the heat gained by paraffin? Heat gained by paraffin is again ms delta T. Its mass is 0.25. Specific I don't know. Delta T is its temperature is rising from 29 to 33. Right? So you will get S itself as joules. Right? Now amount of heat gained should be equal to amount of heat lost should be equal to amount of heat gained. That means S is equal to 2926. Clear? Simple? Right? Moving on to some more smaller topics, because I don't want to go to the larger topics since we have only 10 minutes more. So that is transmission of heat. The next class we will include, or I will include more numerical section. Okay. So transmission of heat, that is how can be heat transported from one place to another. See, there are three forms, that is conduction, convection and radiation. See, in solid materials heat transfers or heat takes place by conduction most of the time. Right, the molecules vibration, right, this is your solid, though when you give heat to one end, so molecules at this end will be moving or vibrating about their equilibrium position like this. They will be vibrating like this, right, and during their vibration they transfer energy to their neighboring person or neighboring molecule, right. That means it has transferred energy to this one. So now this molecule will start to vibrate, so they make the other closer molecule to vibrate like this. The heat will be transferred from this end to this end. And this type of motion or this type of transmission of heat is known as what? Conduction. Simple, right? The next type, which is convection. Convection, right? That is a process in which the heat is transported in fluids, right? So conduction happens in solids, means convection happens in the case of fluids, liquids as well as gases. Okay. So in convection, the transfer of heat takes place by transport of matter. It is in the form of motion of particles with more than average energy to other cooler regions. That is, suppose we are considering a liquid in a container. right? And I'm heating this entire system. So the molecules in the lower layers are heated and its density decreases. As a result, these molecules will rise up, right? Clear? And the heavier ones, or which is at the topper section were heavier one, they come down, right? And now they will be heated and they become less denser, and they try to move up again. The molecules which are above try to move down, right? This continuous movement of molecules takes place, and during this, and this is known as convection. Clear? And this type of waves, etc., you can learn. Actually, I would recommend to read the example of convection is given in your textbook. How the, when you consider earth, right, in this equator region, that is the region which gets heated easily, right? So here the air which is around this equator will get lesser denser, right? So they try to move to a surface or area. The air will no, move to the area, try to move up, right? Whereas the wind which is in the this region, right, they will start to feel what heavy, right? So they will be moving in this region, right? So the air in the equator which is getting heated start to go less, have density. Less density mean they rise up, and the denser air from the tropical region, or the at the polar regions, try to move from there to here, right? The next 6 months, what happens then? Here the heat will be high, and here the heat will be less. Okay. Another way of convention, or another example of convention we can talk about, is sea breeze and land breeze. See, this is all natural phenomena. There is artificial phenomena of convection which we learn during live class. I will discuss it. Okay. So what do you mean by sea breeze and land breeze? It's a natural phenomena, means it happens, right? So for explaining both the cases, we are going to draw two things. This is land and this is sea, right? So let us talk about sea breeze. Sea breeze happens during day, that is very important, and land breeze happens during night. So the sun is heating up both land and sea, right? I'm so sorry for the disturbance. Right. Now the sun is heating up both sea surface and the land, but as the sea is having higher heat capacity, it absorbs much of the sun's energy, but it gets warmed up very slow when compared to the land. As a result, the temperature above the land, right, it rises, right, and heats the air in the atmosphere. Right, this is heating, that means this air will be heated, and this air goes up and it is heating up the atmosphere about it. Now this warm air is now less dense, and hence it expands, and it is having creating a low pressure area of this over this section, right? And this land area, this I can say sea coast, is having now lower pressure, right? Whereas here the sea, it is having what? Higher pressure, right? So there is an air pressure difference, right? So the air will starts to flow from sea to land, right? Why? Here density higher, here lesser density. So lesser density air occupies here, and higher density tries to go over here, right? So more of less, I can say the air or the wind will be moving higher from the sea to land. That's why it is called sea breeze, right? Because here the density of air is higher, right? So the density higher means there here higher pressure, here lower pressure, right? Clear? Here the density becomes less. Density less means it is expanding, lower pressure, then that means here higher pressure. Now the opposite happens during land breeze, right? Land breeze, in the sense it is happening during night, right? So during night means, let's just remove this section, right? I'm drawing land and the sea here, right? See, the phenomenon here is reversing. Now as the sun is setting, the land and the sea starts cooling down, but the land will quickly lose its heat, right, when compared to the water due to the difference in the heat capacity. Now consequently the temperature of the sea is now higher, which creates an air which here will be getting heated. So here will be the lower pressure section. So it's similarly opposite here, higher pressure section, right? That means the air will flow from higher pressure to lower pressure. So from land to sea, the air goes. That is known as land breeze. Right? So there are two examples we have taken here. Right? I've taken it separately because it is very important to understand the examples of convection. And forced convection is what I will deal later on. And there you will learn Newton's law of cooling, etc. Okay, so we'll talk about it in the next class.